Imagine staring at the night sky, where every twinkling light follows rules we've etched in stone. Fusion fights gravity. Stars live, die, and sometimes swallow themselves whole. But what if one hidden type of star laughs at all that, nesting impossibly inside itself, like cosmic Russian dolls, powered by the very force ripping the universe apart? This isn't sci-fi. It's the wildest challenge to physics yet. If mind-bending cosmic secrets keep you up at night, smash that like button and subscribe, because what comes next will completely shock you. Prepare yourselves. We begin. Picture this. You're gazing up at the sun on a clear day, that massive, fiery orb dominating our sky. And it's easy to take for granted how it just hangs there, steady and reliable, pouring out light and warmth without a second thought. But beneath that calm exterior, a colossal battle rages every single second. A delicate dance between forces that could either sustain life across an entire solar system or snuff it out in an instant, if things tipped even slightly off balance. At the heart of it all is gravity, that relentless pull we all feel on Earth, but amplified to insane levels in a star like our Sun, where the sheer mass, about 330,000 times greater than our planet, tries to squeeze everything inward toward a crushing core, threatening to collapse the whole thing into a dense, lifeless ball smaller than a city. Yet, it doesn't happen, not for billions of years, because there's a counterforce at play, a powerhouse of nuclear fusion churning deep inside, where temperatures soar to 15 million degrees, and pressures force hydrogen atoms to smash together in a frenzy, forging helium and unleashing energy so vast it radiates outward like an unstoppable wave. This isn't just heat, it's pressure, raw and photon-driven, bouncing through layers of plasma in a chaotic maze that can take those light particles thousands, even hundreds of thousands of years to escape, finally bursting free as the sunlight that bathes your face. That outward shove perfectly offsets gravity's inward grip, creating equilibrium, a cosmic standoff where neither side yields, keeping the sun puffed up to its enormous size, about 109 times wider than Earth, with a volume that could swallow over 1 million worlds like ours. Think about how wild that is. Stars aren't solid rocks or even fluffy clouds. They're seething balls of gas, mostly hydrogen and helium, held together not by any tangible glue, but by this invisible tug-of-war. And our sun has been locked in it for roughly 4,600,000,000 years now, fusing away at a rate of 600 million tons of hydrogen every second, converting a tiny fraction, less than 1%, into pure energy through Einstein's famous mass-energy equivalence, where a minuscule loss in mass translates to an explosion of power. Without this balance, the sun would either explode outward in a premature blast or implode violently, but instead, it maintains stability, its outer layers cooler at around 5,500 degrees compared to the core's inferno, allowing convection currents to carry heat from the depths to the surface, where magnetic fields twist and tangle, sometimes erupting in solar flares that send charged particles hurtling toward us at speeds up to 2 million miles per hour. It's this very mechanism that powers everything we know, life on Earth, the orbits of planets, the very rhythm of days and nights. And yet, it's all so precarious, reliant on the star having just the right mix of elements from the Big Bang's leftovers, with trace amounts of heavier stuff like oxygen and carbon sprinkled in from previous stellar generations, adding flavors to the fusion recipe. As you ponder that, consider how fusion isn't uniform. It ramps up in the core, where density hits 150 times that of water, then tapers off in shells around it, creating onion-like layers that shift over eons, slowly converting the sun's hydrogen fuel reserves, which make up about 70% of its initial mass, into helium, gradually altering its composition and nudging the balance ever so slightly toward gravity's favor. But for now, in this middle age of stellar life, everything hold, the radiation pressure from fusion photons, trillions upon trillions generated per second, propagating outward through radiative and convective zones, where in the outer third, hot plasma bubbles rise like boiling soup, carrying energy to the photosphere, that thin, roiling surface we see as the sun's edge. Imagine diving into that soup. You'd be vaporized instantly, but theoretically, there's no hard ground to land on. Just endless sinking into denser gas until fusion's push halts you. A reminder of how stars defy our earthly intuitions, existing as self-regulating furnaces in the void. This equilibrium isn't unique to the sun. It's the universal rule for main sequence stars, those hydrogen-burning powerhouses that populate the Milky Way. From tiny red dwarfs a tenth, the sun's mass, sipping fuel so slowly they might shine for trillions of years, to behemoths 100 times more massive, guzzling hydrogen at rates that doom them to mere millions of years of life. Before the balance inevitably breaks, take a star like Rigel in Orion, blazing blue-white, with a mass 18 times the sun's, its fusion core raging at 30 million degrees, producing energy equivalent to billions of nuclear bombs every second. Yet still locked in that same push-pull, its outer winds howling at thousands of kilometers per second, shedding mass that will one day seed new stars. Or consider Proxima Centauri, our nearest stellar neighbor, a feisty red dwarf 1/8 the sun's mass, its fusion subdued but persistent, flares occasionally lashing out with X-rays that could strip atmospheres from close-orbiting planets, all while gravity claws at its tiny frame, balanced by a fusion output, a fraction of the sun's but enough to keep it from cooling into obscurity. What makes this balance so captivating is how it emerges from chaos. Quantum tunneling allows hydrogen nuclei to overcome electrostatic repulsion and fuse, despite the odds, releasing gamma rays that downgrade through scattering collisions into visible light. A process so inefficient in terms of speed, yet so effective in sustaining the star's girth. Delve deeper, and you'll find that this isn't just physics. It's the forge of elements, where over time, as hydrogen depletes in the core, down to about 10% remaining in the sun's case today, the star begins to contract slightly, heating the surroundings and igniting a helium flash in more massive stars. But for sun-like ones, it's a slow evolution toward the red giant phase, where the outer envelope expands dramatically, potentially engulfing inner planets like Mercury and Venus in 5 billion years. Yet, even in that future turmoil, the core's fusion will adapt, fusing helium into carbon and oxygen, releasing fresh pressure to stave off collapse a while longer, illustrating how stars are dynamic, ever-adapting engines, their balances shifting like tides under gravity's moon. Astronomers track this through spectroscopy, decoding light to reveal compositions, hydrogen's Balmer lines strong in young stars, helium's signatures emerging later, and heliosysmology, studying sunquakes to map internal densities, confirming the fusion zones with exquisite precision, down to variations in sound waves propagating at 350 kilometers per second. It's these insights that make ordinary stars far from ordinary. They're the universe's alchemists, turning primordial gas into the building blocks of planets and life, all sustained by that fragile equilibrium where one wrong fluctuation could unravel it all. But what happens when the fuel runs critically low? When the core's hydrogen dwindles to nothing and fusion sputters, that's when the real drama unfolds. As gravity, long held at bay, begins to assert dominance, squeezing the star's heart and setting the stage for remnants that defy imagination even more than the living star itself. For smaller stars, the end is a quiet fade into a white dwarf. But to understand why, we must explore those quantum safeguards that step in when nuclear fire dims, preventing total obliteration and birthing a new chapter in stellar archaeology. As we peel back these layers, you'll see how the ordinary gives way to the extraordinary, hinting at even stranger possibilities lurking in the shadows of collapsed cores, where physics starts to bend and what we think we know about stars unravels. Thread by thread, our sun, for all its familiarity, is just the gateway, a stable beacon illustrating the fusion gravity ballet that every star performs, but with masses varying from a fraction to dozens of times its own, each tweaking the performance, Low-mass stars like Dwarfs, with convective cores mixing fuel evenly for longevity. High-mass O-type stars with radiative cores burning hot and fast. Their balances teetering on the edge from the start, winds eroding them before fusion even peaks. Consider the Pleiades cluster, young hot stars still in their prime, their spectra screaming youth with strong hydrogen absorption, while ancient globular clusters host red giants on the brink, their expanded atmospheres cool and dusty, betraying the inward contraction of cores long past hydrogen's prime. This life cycle isn't random, it's dictated by initial mass, that single parameter branching paths from dwarf to giant, from quiet ember to explosive supernova, all rooted in the same equilibrium we see today in the Sun, where surface granulation, those boiling cells 500 miles across, marks the convective churn, and prominences arch millions of miles high, sculpted by magnetic fields born from the dynamo effect of rotating plasma. Dive into the numbers spelled out. The Sun converts 4 million tons of mass into energy per second, yet loses only a hair's breadth in radius over human timescales. Its equilibrium so robust that variations like the 11-year solar cycle, sunspots peaking, activity surging, barely dent the overall balance, though they do influence Earth's climate subtly through cosmic ray modulation. Imagine the scale. If the Sun were hollowed out and filled with Earths, it'd hold 1.3 million, yet that volume is mostly empty space at atomic scales, electrons and nuclei, dancing in a plasma state where fusion occurs via proton-proton chains, 4 hydrogen nuclei merging stepwise into 1 helium, positrons and neutrinos byproducts, the latter streaming out unimpeded at light speed, carrying away clues to the core's secrets that detectors like Super Kamiokande now capture. This neutrino flux, once a puzzle in the 1970s when counts fell short, resolved by oscillations, revealing their flavor changes, underscores how even the Sun's balance hides subtleties, quantum effects, ensuring fusion proceeds despite barriers. As stars age, this balance evolves. In the Sun's future, core contraction will balloon the radius to over 200 times current luminosity, spiking 1,000-fold, turning it into a bloated red giant that could scorch Earth's oceans dry, long before the core ignites helium. But for now, it's the exemplar, teaching us that stellar stability is no accident, but a symphony of nuclear, gravitational, and electromagnetic forces, each note precise, each harmony essential. Venture to other stars, and the variations dazzle. Sirius, the dog star, twice the Sun's mass, burns hotter at 25,000 degrees surface, its fusion roaring through CNO cycles, dominant in heavier stars, where carbon acts as catalyst, efficiency soaring, but lifespan halving to 1 billion years. Betelgeuse, a red supergiant, already post-main sequence, its balance long shifted, outer layers drifting away at 15 kilometers per second, revealing a core fusing silicon now, on the cusp of supernova, in mere millions of years. These examples illuminate the universality, no matter the size. The equilibrium holds via fusion pressure until it can't, and that's the pivot to death's door, where white dwarfs emerge as cooled remnants, their degeneracy pressures, electron-based for low mass, propping up against gravity's final assault, densities hitting a ton per cubic centimeter, surfaces at 100,000 degrees initially, fading to black dwarf invisibility over trillions of years. Yet even here limits lurk, exceed 1.4 solar masses, and electrons can't hold, forcing further collapse to neutron realms. But that's a tale for when ordinary stars' balances shatter irreparably, opening vistas to the exotic ends that make astrophysics endlessly thrilling. So as we leave the Sun's steady glow, remember its lesson: balance begets longevity. But exhaustion invites transformation. And in those transformations lie the seeds of universe-shaping wonders, from element factories to gravitational wave symphonies, all starting with that simple stellar standoff high above our heads. Imagine the moment when a star like our Sun, after eons of that fierce fusion battle we just explored, finally exhausts its core hydrogen, the nuclear furnace flickering out like a candle in the wind, leaving behind a core that's mostly helium ash, no longer generating the radiant pressure needed to hold back gravity's unyielding squeeze. And suddenly, the equilibrium shatters, the outer layers starting to drift inward as the star contracts, heating up the surrounding shell where fresh hydrogen fusion ignites in a thin layer, causing the whole envelope to puff outward dramatically, transforming the once modest sun into a swollen red giant, its surface cooling to a ruddy glow around 3,000 degrees, while the radius balloons to swallow Mercury's orbit, maybe even Venus, scorching any nearby worlds with intense heat that could boil oceans and strip atmospheres in a cosmic catastrophe. But deep inside, the core keeps shrinking, fusing helium into carbon and oxygen in a sudden flash for sun-like stars, releasing a burst of energy that briefly stabilizes things before gravity reasserts, eventually shedding the outer layers in a beautiful planetary nebula. A glowing shell of gas illuminated by the hot core beneath, expanding at 10 kilometers per second, and painting the sky with colors from ionized elements, red from hydrogen, green from oxygen, blue from helium, all while the remnant core, stripped bare, settles into its final form as a white dwarf, a dense ember, no larger than Earth, yet packing the mass of our sun, its surface gravity, 1,000,000 times stronger than here, so intense that a raindrop falling onto it would hit with the force of an atomic bomb. And this isn't some rare oddity, but the fate awaiting roughly 97% of stars, those under 8 times the sun's mass, turning them into these compact fossils that slowly cool over billions of years, radiating away their heat until they become invisible black dwarfs, the universe's stellar graveyards, dotting the galaxy like forgotten jewels. What props up this white dwarf against total implosion, you might wonder, since fusion has quit and there's no more outward push from nuclear reactions? And the answer lies in the weird world of quantum mechanics, specifically electron degeneracy pressure, a force born from the Pauli exclusion principle, that unbreakable rule stating no two electrons can share the exact same quantum state, meaning in the crushing densities of a collapsing core, reaching 10 to the 6th grams per cubic centimeter, they pack together like sardines in a can, but can't overlap in their energy levels, creating an immense outward resistance that's purely statistical, independent of temperature. So even as the dwarf cools from a scorching 100,000 degrees to room temperature over trillions of years, this quantum barrier holds firm, keeping the star puffed to about Earth's size despite its solar heft, a teaspoon of its material weighing as much as an elephant, and this pressure scales with density in a way that makes white dwarfs incredibly stable, their interiors a degenerate electron gas where atoms are smashed flat, nuclei swimming in a sea of delocalized electrons, all governed by Fermi-Dirac statistics that predict this floor against further squeeze. But here's the gripping twist. There's a hard limit to how much mass a white dwarf can shoulder before this quantum shield buckles, a boundary etched into astrophysics by the brilliant Indian scientist Subrahmanyan Chandrasekhar in the 1930s during a long sea voyage where he crunched the numbers by hand, realizing that as mass climbs, the dwarf shrinks to maintain balance, but relativity creeps in at extreme densities, tweaking the electron energies and allowing more to fit before exclusion kicks hard, yet eventually, for masses exceeding about 1.4 times the sun's precisely, 1.44 solar masses in refined calculations, the pressure can't counter gravity anymore. Electrons forced into relativistic speeds, where their resistance softens and the whole structure teeters on collapse. This Chandrasekhar limit, acting like a cosmic weight class, separating stable embers from those doomed to heavier fates. And it's not just theory, we see it in binaries, where white dwarfs secrete mass from companions, inching toward that threshold until they detonate as Type Ia supernovae, their light standardized for measuring cosmic distances, helping map the universe's expansion and even discovering dark energy's push in the late 1990s. Picture a white dwarf in the wild, like Sirius B, the faint companion to that bright dog star, discovered in 1862, but only confirmed as a dense oddity in 1919, with a mass 1 solar and radius, half Earth's, surface at 25,000 degrees, glowing white-hot, yet cooling steadily, its spectrum showing heavy element lines from past fusion. And as it orbits, gravitational effects on Sirius A reveal its heft, proving the degeneracy reality without direct imaging, until Hubble snapped it in the 2000s, a tiny dot against the glare, symbolizing how these remnants hide in plain sight, outnumbering main sequence stars in old clusters like Messier 13, where surveys count hundreds of white dwarfs per 1,000 giants, their ultraviolet glow betraying youth among the red ancient ones. Delve into the formation drama as the red giant phase peaks. Pulsations shake the atmosphere, driving winds that carry away half the mass over tens of thousands of years, leaving the exposed core to settle, initially with a thin hydrogen or helium layer, but over time, gravitational settling sinks heavier elements inward, creating stratified interiors, carbon-oxygen cores for sun-like progenitors, helium for lower mass red dwarfs that skip helium flash. And this composition affects cooling rates, with oxygen-rich ones fading slower due to lower heat capacity, while magnetic fields, frozen in from the progenitor, can make them into peculiar types with strong polar caps, emitting X-rays as they spin down, or even cataclysmic variables, when siphoning hydrogen from neighbors, igniting surface bursts that light up the sky temporarily. The quantum mechanics here gets even more fascinating. In non-relativistic regimes, pressure goes as density to the 5/3 power, a stiff equation of state that lets models predict radii inversely, with mass cubed to the third. Wait, no. Radius scales as mass to the -1/3, so heavier dwarfs shrink, packing tighter until relativity, at speeds near light, softens it to density to the 4/3, reducing support and setting the 1.4 limit, where the star would need to shrink to a pinpoint. But instead, if paired, it triggers runaway fusion in accreted layers, exploding with peak brightness, tied to that mass threshold, making them cosmic standard candles, their light curves fading predictably over weeks, luminosities pegged at 2 billion times the sun's for a moment, outshining galaxies briefly. Think about the journey. A 1 solar mass star like the sun will end as a 0.6 solar mass white dwarf, after losing outer fluff, its core never exceeding the limit. But edge cases near 8 solar masses push closer, fusing up to neon magnesium before shedding, remnants hovering near 1.2 solar masses. And in clusters, we spot these with cooling ages matching the population. 100 million years old ones, still hot at 10,000 degrees. Billion-year veterans dimmer, their spectra evolving from ultraviolet to infrared dominance in astrocosmology. Like with Procyon b, probes interiors via pulsations, waves traveling at sound speeds, adjusted by degeneracy, revealing convection zones or crystallization as they cool below 1,000,000 degrees Kelvin, where carbon lattices form like diamond interiors, boosting conductivity and slowing fade, potentially making old dwarfs into solid worlds of pure carbon, exotic gems floating in space. This limit isn't abstract. It echoes in evolution's branches. Stars below half solar mass become helium white dwarfs directly after billions of years on the main sequence, skipping giants, their low gravity letting them hold on to envelopes longer, while intermediate ones, like 0.8 solar, get the full red giant show. And the 1.4 cap explains why no lone white dwarf succeeded. Naturally, though binaries can flirt dangerously, like Nova Cygni in 1876, recurring every few decades as the dwarf grazes the edge, or the ultimate Type Ia, detonating fully when hitting the limit, leaving no trace, just dispersing iron group elements that seed future stars, closing the cycle. As you visualize these cooling cinders, consider their role in the galaxy. They tug on orbits subtly, their combined mass rivaling visible stars in the disk. And in dense environments like globulars, close encounters can disrupt them, flinging material or merging to form hotter hybrids. While microlensing events occasionally betray their presence, a star's light, briefly dimmed, as a foreground dwarf passes, durations from hours to days revealing masses and distances, with surveys like Gaia cataloging millions, mapping the white dwarf population's age distribution to trace star formation history back 10 billion years. The exclusion principle's power shines here. Electrons spin and momentum forbidding closer packing, a consequence of wave functions not overlapping, yet in extreme cases near the limit. Inverse beta decay. Electrons capturing protons to make neutrons, hints at the transition to neutron stars, but for white dwarfs, it stays electrons ruling the roost, their pressure scaling as h-bar squared over electron mass times density to the 5/3, where h-bar is Planck's constant divided by 2 pi, that fundamental quantum tick keeping the cosmos ordered. Engagingly, these dwarfs aren't inert. Some host planets, like those around Van Manen, 2, a 100,000-degree youth with rocky worlds, inferred from wobbles or pulsar-like, if spun fast, though rare, and in the far future, as the universe ages, they'll dominate, outlasting red giants by cooling to black. But before that, they whisper secrets of progenitors, mass from initial 1 to 8, solar mapping to final 0.01 to 1.4, a direct readout of stellar history, and helium flashes in low metallicity stars, like in early universe analogs, produce brighter bursts, tweaking remnant masses. The Chandrasekhar saga adds human drama. Young Subramanian, doubting his own calc, faced skepticism from giants like Eddington, who favored energy sources over degeneracy, but observations vindicated him, earning the Nobel in 1983. And today, refined limits account for rotation or magnetic effects, slightly raising the cap to 1.44 for non-spinning, but the essence holds, a boundary where quantum defiance meets gravitational tyranny, and beyond it, for stars 8 times solar or more, the core surpasses even neutron thresholds. But wait, that's the bridge to denser realms, where white dwarf's story ends, not with a whimper, but a warning, hinting that when limits break, nature invents new pressures, electron to neutron transitions. In the next chapter of Collapse, pulling us deeper into the stellar underworld, where ordinary deaths birth monsters that warp reality itself. Yet, linger on white dwarfs a moment more. Their atmospheres, thin hydrogen or helium layers, can accrete metals from space winds, detected as absorption lines, and cooling curves model their luminosity evolution, from absolute magnitude 10 at birth to fainter than 20 after 10 billion years, with helium ones cooling slower due to opacity, and in cataclysmic binaries, they drive novae, not full explosions, recycling mass in disks that light up X-ray binaries, or AM Hercules systems with synchronized spins from field locking, all showcasing how these limits don't just cap mass, but catalyze galactic chemistry. They're supernovae, forging iron peaks that measure Hubble constant tensions today, fueling debates on expansion rates that tie back to dark energy mysteries we'll circle later. In vivid scenes, envision the planetary nebula phase preceding the dwarf, the sun's future envelope, puffed to 1 astronomical unit radius, pulses with instability, helium shell flashes every 100,000 years, each heaving more mass outward until 80% escapes. the core exposed at 10,000 kilometers across, initially surrounded by a wind at 100 kilometers per second, sculpting bipolar shapes in asymmetric ejections, like the Ring Nebula's hourglass, glowing for 20,000 years before fading, leaving the white dwarf at its heart, a 10 solar mass loser, now 0.6 solar, gravity at 10 to the 8th times Earth's, time dilation making clocks tick slower by factors near 1 plus escape velocity, squared over 2c squared, where c is light speed, subtle but real, for orbiting probes in theory. This endpoint captivates because its quiet revolution, from life-giver to dense relic, quantum rules eternalizing the corpse, limits like Chandrasekhar's, the guardrail preventing chaos, yet when breached in binaries, birthing supernovae that outshine quasars for weeks, their remnants enriching interstellar medium, with nickel-56 decaying to cobalt, powering the light curve, and spectra revealing silicon lines at maximum, confirming the explosion mechanism as carbon detonation in the core, a thermonuclear runaway, sparked by compressed temperatures over 1 billion degrees. Across the cosmos, white dwarfs in the halo, old and metal-poor cool uniformly, their distribution tracing dynamical heating from galactic tides, while in the bulge, younger populations pulse with novae, and surveys, like the European Southern Observatories, VLT, capture their infrared echoes, mapping dust from progenitors. The exclusion's elegance lies in its universality. No temperature dependence means they cool monotonically, unlike stars with radiative losses and crystallization at log density, around 10 releases latent heat, pausing the fade like a stellar pause button, predicted by models matching observations in Heidi's clustered dwarfs. As we wrap this tale of dying lights, feel the pull toward escalation. White dwarfs hold the line for modest stars, but when cores bulk to 1.4 and beyond, degeneracy yields, electrons merging with protons into neutrons under beta equilibrium, birthing the next extreme, where pressures ratchet up to atomic nuclei densities, and the story hurtles toward spins that defy comprehension, setting the stage for why some collapses stop short of black hole voids, teasing those exotic alternatives that redefine stellar ends entirely. Imagine the cataclysmic crescendo, when a star far more massive than our Sun, say 8 to 25 times its heft, reaches the end of its furious fusion frenzy, having blazed through hydrogen, helium, carbon, oxygen, and even silicon in rapid succession, its core layering like an onion of heavier elements until iron builds up, that point where fusion no longer releases energy, but guzzles it, tipping the scales decisively toward gravity's victory. And in a heartbeat of stellar time, mere seconds in human terms, the core implodes under its own weight, the outer layers crashing inward at a fraction of light speed, rebounding off the unyielding neutron-rich heart in a shockwave that rips through the star, igniting a supernova explosion so brilliant it can outshine an entire galaxy for weeks, hurling elements from helium to uranium into space at 10,000 kilometers per second, seeding the cosmos with the stuff of planets and life, while the core, stripped to a ball about the size of a city, 20 kilometers across, compacts to densities where a sugar cube's worth outweighs Mount Everest by billions of tons, transforming protons and electrons into a soup of neutrons held apart by yet another quantum marvel, neutron degeneracy pressure, where the exclusion principle now applies to these neutral particles, their wave functions refusing to overlap in the same quantum state, creating a rigid floor against further crush that makes the white dwarf's electron version seem tame. And this is the birth of a neutron star, not a gentle fade like the dwarf, but a violent survivor of apocalypse, spinning potentially hundreds of times per second, if angular momentum conserves from the progenitor, its surface a crust of superfluid neutron matter, a few meters thick over a denser liquid interior, temperatures initially at 10 billion degrees, but cooling rapidly through neutrino emission, those ghostly particles carrying away heat without interaction, until the star settles into a glowing ember of extreme physics. What makes neutron stars such pulse-pounding enigmas is their sheer intensity. Gravity at the surface, 200 billion times Earth's, so fierce that light from the poles redshifts noticeably. Time dilates for observers nearby, and a marshmallow dropped onto it would explode with nuclear force, while the magnetic fields, amplified by the collapse's dynamo, can reach quadrillion Gauss, twisting plasma into jets or trapping particles in death spirals that emit gamma rays, turning some into magnetars, those rare beasts that flare with energy, rivaling the sun's lifetime output in a tenth of a second, quaking their crusts with starquakes that ripple space-time subtly, detectable across the galaxy as bursts lasting milliseconds. Picture the formation frenzy in the supernova's heart as the core surpasses the Chandrasekhar-like limit for neutrons. Around 2 to 3 solar masses, the implosion halts at nuclear density 1 × 10 to the 17th grams per cubic centimeter, where strong nuclear force joins degeneracy to resist. The equation of states stiffening as neutrons pair into superfluids, vortices, pinning to the lattice in the crust, allowing glitches and spin down as they unpin suddenly, slowing the rotation by tiny fractions, like the famous Vela pulsar dropping a few times per year, its beam sweeping Earth every 89 seconds. A lighthouse from 12,000 light-years away, discovered in 1968 as the first radio pulsar, initially mistaken for little green men signals by Jocelyn Bell Burnell, who shared the Nobel with her advisor, opening the door to neutron star zoo. Delve into that spin. A newborn might whirl at 1,000 Hz from conserved angular momentum, but magnetic dipole radiation breaks it over eons, torquing at rates proportional to field strength squared over moment of inertia, with young ones like the Crab pulsar at 30 rotations per second. Born from the 1054 supernova, recorded by ancient astronomers, its nebula glowing from the pulsar's wind slamming into ejecta at half-light speed, synchrotron radiation painting it green across the sky, while older pulsars fade to radio silence. After 10 million years, their beams narrowing as fields decay, but millisecond ones, recycled in binaries, spin up to 700 Hz by accreting angular momentum from companions. Their stability so precise, they rival atomic clocks, used in pulsar timing arrays to detect gravitational waves from supermassive black hole mergers, ripples in space-time washing over Earth every few years, a cosmic hum revealed in 2023 by Nanograv collaboration. The breaking point looms large, that Tolman-Oppenheimer-Volkoff limit, theorized in the 1930s by those physicists crunching general relativity's hydrostatic equilibrium, where pressure gradients balance gravity in curved spacetime, showing that unlike white dwarfs' Newtonian scaling, relativistic effects soften neutron support beyond 2 solar masses. The exact cap fuzzy at 2.1 to 2.8, depending on the equation of state, whether it's soft, like lab nuclei, or stiff with hyperons or quark matter. But observations pin it around 2 solar masses, as in the Hulse-Taylor binary PSRB 1913+16, where orbital decay from energy loss to gravitational waves, first indirect proof of Einstein's ripples, matches neutron star masses at 1.4 each, earning the 1993 Nobel, while heavier ones, like PSRJ 0740 plus 6,620 at 2.08 solar masses, measured via Shapiro delay in its white dwarf companion's light bending, push the edge, and exceed that, and collapse resumes. No known pressure holding against the tidal forces that would shred even neutrons into a singularity, birthing black holes in the final act. Engagingly, neutron stars aren't uniform spheres. Equations allow mountains, kilometers high from elastic crusts, bulging equatorially from rotation, up to a kilometer for fast spinners, and in binaries, they devour partners, forming X-ray sources where accretion disks heat to millions of degrees, flaring as matter hits the surface at 1/3 light speed, or in low-mass X-ray binaries, thermonuclear bursts from piled hydrogen igniting mimicking novae, but on neutron crusts, while quark stars, a hypothetical extreme where deconfined quarks provide stiffer support, might lurk if the limit's higher, their surfaces, glitching uniquely or converting to strange matter that contaminates anything it touches. A sci-fi contagion debated in papers. Visualize the interior odyssey from the 100-meter crust of neutron-rich nuclei in neutron drip phase, where free neutrons leak out below densities of 10 to the 11th grams per cubic centimeter, to the outer core's superfluid neutrons at 10 to the 14th, pairing in spin-up states for zero viscosity, allowing glitch recoveries, then inner core puzzles with possible pion or kaon condensate softening pressure, or free quarks at 10 to the 15th, a transition to hybrid stars blending neutron and quark phases, densities rivaling the early universe microseconds after the Big Bang, where electroweak forces unified. And here, in these stellar labs, we probe those epochs indirectly through cooling curves, fast initial neutrino burst, dropping temperature from 10 to the 11th Kelvin in seconds, then slower photon escape over thousands of years, with isolated ones like Jaminga, a gamma pulsar from a 1,000,000-year-old supernova, now radio quiet but beaming high-energy particles, its proper motion across the sky, a bow shock in interstellar gas. The magnetic drama captivates standard pulsars at 10 to the 12 Gauss, but magnetars at 10 to the 15th stir their fields decaying over 10,000 years, powering outbursts from crust fractures, releasing stored energy, like SGR 1806-20, flaring in 2004, so bright it ionized Earth's atmosphere temporarily, or soft gamma repeaters cycling every few minutes, while old magnetars might seed anomalous X-ray pulsars, their torque from propeller effects on fallback disks, and all this from seed fields of progenitors amplified thousandfold in collapse, frozen flux lines, twisting the star into oblate shapes. Across the galaxy, about 1,000 radio pulsars cataloged, but millions estimated, their distribution tracing supernova rates over cosmic time, with young populations in arms and old disk ones scattered, and in globular clusters, recycled millisecond pulsars, dense as 10 per cluster, enabling array tests for wave backgrounds, while isolated fast ones, like PSRJ 1748-2446, add at 716 Hz. The fastest known showcases accretion's spin-up limit before centrifugal breakup. The breaking point's tension builds in observations. No confirmed neutron stars above 2.5 solar masses yet, but candidates like the Black Widow pulsar with a 2.01 companion imply core masses near 3 if evolved, and kilonova GW 170817. The neutron star merger detected in 17 spewed heavy elements via our process, but if progenitors were 2 solar each, their merger mass 4 exceeded the limit, forming a black hole promptly, waves chirping up to merger in Gould's cosmic forge, while softer equations allow hypermassive stars up to 2.5 supported temporarily by thermal pressure before settling or collapsing. This extremity isn't just numbers, it's the universe's forge refined. Neutron stars churn out our process elements in mergers, gold and platinum from neutron capture cascades, and their winds sculpt supernova remnants like the crab's filaments, magnetic reconnection, accelerating particles to peta-electron volts, cosmic rays bombarding Earth, while glitches map superfluid dynamics, sudden spin-ups from vortex avalanches, restoring angular momentum, lost to crust, fractions of a part in 10,000 per event, recurring predictably, in some like PSR B0531 plus 21. As we trace these titans, feel the inexorable pull for cores under 2 solar masses post-supernova. Neutron degeneracy reigns, birthing these spinning, beaming behemoths that pulse with radio, X-ray, Gamma signatures, their light curves folded to reveal periods from milliseconds to seconds. Dispersion measures gauging interstellar electron columns along lines of sight, distances from parallax or associations with remnants, building a census that illuminates stellar evolution's violent branch. Yet, push to 25 solar masses and beyond, and even neutrons falter. The Tolman-Oppenheimer-Volkoff equation, yielding unstable solutions where pressure gradients can't match relativistic gravity. The star imploding fully, no rebound, straight to event horizon and singularity. But that conventional end chafes against infinities, sparking whispers of alternatives we'll chase next, where collapse might halt without voids. Exotic pressures, weaving new threads in the stellar tapestry, hinting that the breaking point isn't absolute, but a gateway to physics' hidden layers, where neutron stars stand as the last bastion before the unknown, their extremes not endings but provocations to rethink the cosmos' darkest hearts. Imagine the ultimate surrender in a star's saga, when even the neutron star's ironclad quantum defiance crumbles under a core mass swelling past 2 or 3 times the sun's. The collapse accelerating unchecked through densities that shred atomic bonds and force fields alike, space-time warping into a funnel so steep that not even light can claw its way out, birthing what we call a black hole, not some empty void, but a region where gravity reigns supreme, defined by the event horizon, that invisible boundary, the Schwarzschild radius for non-spinning ones, shrinking to a mere 3 kilometers across for solar mass equivalents, yet swelling to billions for galactic behemoths, a point of no return, where infalling matter spirals in with tidal forces, stretching it like cosmic spaghetti before crushing it beyond recognition. And from afar, it appears as a silhouette against starlight, bending rays into a glowing ring, while devouring companions in fiery accretion, disks that heat to millions of degrees, spewing X-rays and jets that carve through space at near-light speeds, powering quasars that once puzzled us as star-like, but now reveal as supermassive hearts of distant galaxies, like Sagittarius A-star in our Milky Way, imaged in 2022 by the Event Horizon Telescope as a fuzzy orange shadow, 38 million kilometers wide, mass 4 million suns, orbiting stars whipping around it unharmed, but doomed in eons, proving black holes aren't just theory, but architects of cosmic structure, merging to grow galaxies and seeding supermassive ones from stellar seeds in the early universe. Their spins aligning disks that birth stars in ordered spirals, and consider how these monsters form not just from single-star deaths, but in pairs, as LIGO's detections show binaries spiraling from wide orbits, tightened by gravitational wave emission, or in dense clusters where captures happen, black holes dancing in trios that fling one away at thousands of kilometers per second, leaving the pair to merge eventually, their waves carrying imprints of asymmetric masses that challenge formation models, hinting at primordial origins in the universe's first minutes, when density fluctuations collapse directly into holes without stars. Yet, peel back the awe, and mysteries swarm like shadows at the edge. What lurks inside that horizon, beyond the firewall debate, where quantum effects might incinerate intruders instantly, or the gentle plunge into oblivion, and the deeper riddle of the singularity, that predicted heart of infinite density and zero volume, where general relativity's equations scream division by zero, curvature blowing up as tidal forces diverge, laws of physics dissolving into nonsense, a mathematical breakdown signaling incomplete theory, much like how Newtonian gravity failed at orbital speeds, demanding Einstein's curved spacetime. But here, no upgrade yet, reconciles it with quantum mechanics, where probabilities rule the small and infinities, spell trouble, hinting black holes might be placeholders for something grander, perhaps strings vibrating in higher dimensions, or loops of space foaming at Planck scales 10 to the negative 35 meters, where discreteness halts the crush. And this isn't mere speculation. Experiments like those at the Large Hadron Collider hunt for extra dimensions through missing energy and collisions, while analog black holes in labs use sound waves and fluids, or light and fibers to mimic horizons, trapping photons and observing Hawking-like radiation, tiny analogs that spark real insights into quantum gravity's elusive blend. This unease fuels the information paradox, a brain twister tossed by Stephen Hawking in the 1970s when he wedded quantum field theory to curved space, calculating that black holes radiate thermally, blackbody spectrum at temperature inversely proportional to mass. Tiny for stellar ones, colder than cosmic microwave background, evaporating over 10 to the 67 years for solar mass, but gargantuan for supermassive, nearly frozen. Yet this Hawking radiation, born from vacuum fluctuations, where particle pairs pop near the horizon, one falls in while the other escapes, carrying energy that slowly shrinks the whole, implies the black body loses mass. But what of the information encoded in the infalling stuff? Quantum states detailing positions, spins, charges that should preserve under unitary evolution, the no-hiding theorem saying data can't vanish. Yet if the whole evaporates fully to nothing, poof, information destroyed, violating quantum sanctity, a clash so profound it spurred decades of debate, from Hawking's initial bet loss to Suskind's holography, proposing all black hole info smeared on the horizon's two-dimensional surface, area, quarter pi squared in Planck units, encoding three-dimensional volume via AD-CFT correspondence, where gravity in anti-de Sitter space mirrors conformal field theory on the boundary, entanglement weaving the illusion of smooth interiors, and dive deeper into that paradox's layers. Early resolutions like black hole complementarity suggested in Fowler and distant views, compatible, but the monogamy of entanglement, where one qubit can't fully entangle with two, doomed it, leading to the AMPS firewall in 2012, positing that to save exterior entanglement, the horizon burns with Planckian fire, breaking general relativity's smooth fall. Yet critics like Maldacena argued eternal traversability through ER equals sign EPR, wormholes equating to entangled pairs, allowing info to tunnel out via replicas. And 2020's Island Prescription by Almhiri and others calculated entropy drops post-page time when half evaporated, restoring unitarity with islands of interior connected to exterior. Computations in toy models, like eternal black holes showing fine-grained entropy, matching unitary expectations, while page curves from psych models of many-body chaos mimic the turnover, and ongoing work probes scrambling how info mixes fast, near horizons, retrievable only by precise measurements, like the Hayden Preskill proposal, where throwing a page in requires decoding the radiation stream, a computational nightmare, but theoretically sound, tying to quantum error correction, where black holes act as cosmic hard drives, horizons as error-correcting codes protecting bulk info. Engagingly, these aren't abstract puzzles. They echo in observations. LIGO's first chirp in 2015, two black holes 30 and 36 solar masses, spiraling in, waves rippling space-time, at frequencies doubling to hundreds per second, energy release, three solar masses in gravitational bursts, confirming no Hare theorem, where holes forget origins, characterized only by mass, charge, spin, their ring-down modes, quasi-normal at specific tones tied to geometry, matching Kerr metrics for rotating ones, and since then, over 90 detections by 2025, including intermediate masses, up to 150 solar from globular clusters, and the nanograv pulsar arrays, 2023 nanohertz background. From supermassive mergers across cosmic history, a stochastic hum from billions of unresolved sources, while electromagnetic follow-ups like the 2017 neutron star merger, GW 170817, lacked a black hole counterpart, but taught our process limits, and 2024's GW 1905 21 paired waves with optical flare, hinting at gas-rich environments for stellar holes. Cygnus X1, the first stellar black hole candidate in 1964, 10 solar masses, pulling gas from a blue supergiant at quarter light speed, X-rays from shocked matter, revealing the invisible tug, its jet collimating to micro-arcseconds via radio interferometry, while microquasars, like SS433 jet plasma, in relativistic beams, processing from frame-dragging near spinning horizons, lens-thurring effect, twisting space like a vortex, and in clusters, intermediate black holes of hundreds solar masses, inferred from dynamical friction or runaway mergers building them, hinting hierarchical growth from seeds post-Big Bang, when direct collapse of massive gas clouds birthed the first quasars, red-shifting to 13 billion years ago, and recent James Webb images of early galaxies with overbright active nuclei suggest these seeds were hefty, perhaps 10,000 solar masses, avoiding the pair instability gap, where stars 20 to 120 solar masses explode fully, leaving no remnant, carving a mass desert LIGO probes with null detections below 5 solar. The singularity's specter haunts deepest, general relativity, dictating geodesic incompleteness, time-like paths terminating in finite proper time, no continuation beyond, yet quantum gravity candidates diverge, string theory's fuzzballs, horizonless tangles of strings resolving curvature without infinities, microstate geometries, like supertubes counting Bekenstein-Hawking entropy, exactly, or loop quantum gravity's bounce, where Planck density halts collapse into white hole expulsion, avoiding infinity altogether, predicting modified ringdowns with extra modes, testable by future detectors, like LISA launching in the 3040s, sensitive to millihertz waves from supermassive mergers, while Penrose's cosmic censorship conjecture guards against naked singularities, those horizonless infinities that expose physics' underbelly, but violations lurk in charged or overspinning models. Kerr parameter, A over M, greater than 1, allowing closed time like curves for time travel. Paradoxes, wormholes, threading to other universes, though stability crumbles under perturbations, keeping the veil intact, for now, and numerical simulations of collapse, like those from 1990's Choptwick critical phenomena, show self-similar cascades near thresholds, echoing phase transitions, while charged dust shells in Einstein-Maxwell theory teeter on nakedness, but often cloak themselves, and higher-dimensional Gauss-Bonnet gravity allows stable naked singularities, but our four-dimensional realm seems censored, preserving predictability. Visualize falling in from afar, the horizon looms serene, but approach, and redshift blue shifts, incoming light to blinding, time slowing as clocks tick slower, by CRT1-R sub says, over R, freezing the faller eternally, to outsiders, while they plunge finite seconds to singularity, spaghettification at kilometers for stellar holes, gentler for supermassive, where you cross unaware, but either way, no escape, the no-hair simplicity masking roiling chaos, thermodynamic entropy proportional to horizon area, Bekenstein-Hawking formula, quarter times area, over Planck length squared, counting microstates if unitary, fueling black hole complementarity, where distant observers see radiation encoding info, infaller experiences smooth till end, perspectives reconciled by holography, and for rotating ones, the ergosphere drags everything into corotation. Penrose process, extracting up to 29% of mass energy by ejecting particles with negative energy orbits, powering blazar's beams aligned with our line of sight, Doppler boosted by factors of 10, while frame-dragging precesses accretion disks, Larmor orbits ionizing gas, into iron lines broadened by Doppler and gravitational shifts, observed in XMM Newton, spectra of holes like XTEJ, 1650-500, mapping spin parameters near maximal. This paradox parade extends to cosmology, supermassive black holes co-evolving with galaxies, feedback quenching star formation via jets, or mergers lighting up with electromagnetic counterparts like GW 190521's kilonova. But for holes, pure waves, and the final parsec problem, where binaries stall before merger, resolved by gas drag or third body assists, while primordial black holes, hypothetical relics from early fluctuations, might explain dark matter if masses asteroid-sized, evaporating today in gamma bursts, or lunar mass for lensing events, though microlensing searches like OG-yield nulls, tightening bounds, and recent 2025 studies from Euclid's satellite suggest PBH fractions under 1% for solar mass, but higher for 10 to the negative 12 solar seeding structure via accretion halos, while the black hole stochastic background from early quasars could imprint on cosmic microwave background polarization, B modes twisted by lensing, though primordial gravitational waves from inflation remain the holy grail. The allure lies in the unknown, black holes as portals, ergospheres of rotating ones dragging frames for energy extraction via Penrose process, bouncing particles off to steal spin, or superradiance amplifying waves. But paradoxes persist. Does evaporation leave remnants with infinite temperature or info intact in correlations? 2024 calculations by Pennington et al. Affirming unitarity via island rule. Yet measuring it demands horizon probes impossible, leaving theory to wrestle, and soft hair proposals by Hawking late in life. Infrared photons clinging to horizons as low-energy excitations, encoding subtle info without disrupting geometry. A gentle fix to the paradox, while entanglement wedge reconstructions in holography visualize interiors from boundary data, suggesting black holes as highly scrambled quantum computers. Their horizons firewalls only in certain bases. In binaries, like LMC X3, 5 to 10 solar black hole with a star, orbital periods, days, eclipses timing mass precisely, while isolated wanderers inferred from Gaia accelerations, or Fermi's gamma bursts from annihilating dark matter in cusps. But the core mystery endures. If singularities signal theory's end, what replaces them? Gravastars or nestars mimicking from outside. No horizon to lose info. Vacuum energy propping stable shells, tying to dark energy's repulsion. A bridge will cross soon, but for now, black holes stand as physics enigmas, devouring light yet illuminating limits. They're paradoxes, not flaws, but invitations to deeper truths, where the universe's rules might bend further than we dare imagine, pulling us from stellar deaths to cosmic rebirths, in ways that challenge every assumption forged in the stars' fiery hearts. And as we gaze at those distant shadows, whether in M87's colossal ring or our galaxy's quiet giant, we sense the veil thinning. Observations, like pulsar black hole binaries, PSRJ 102 3 + 0031, where a millisecond pulsar orbits a probable low-mass hole, timing tests of strong field gravity via periastron advance, matching Kerr predictions within percent, or future LISA's supermassive mergers resolving ring-downs to probe quantum deviations, all pushing toward that day when paradoxes yield to revelation, redefining not just stars' ends but the fabric of existence itself. This unease with black holes' shadowy paradoxes has long whispered to physicists that there might be another path for collapsing stars, a detour around singularities and event horizons that keeps the math clean and the universe sensible. And that's where exotic stars burst onto the scene, not as wild fantasies, but as elegant solutions plucked straight from the equations of general relativity, challenging the finality of black hole endings with structures that mimic their gravitational grip while dodging the infinities inside. And at the forefront of this revolution stands the Gravistar, short for gravitational vacuum star, a concept that first flickered in the minds of theorists back in the early 2000s, building on older ideas from the 1930s, when Richard Tolman, J. Robert Oppenheimer, and George Volkoff laid down the Tolman-Oppenheimer-Volkoff equation, that powerhouse formula describing how pressure gradients in a star balance against gravity's curve in space-time, normally yielding stable solutions for ordinary stars, but opening doors to weirdness when you tweak the ingredients, like allowing negative pressure at the core, not the kind that pushes out, but a peculiar pull that's actually repulsive on cosmic scales, tied to vacuum energy, the same elusive stuff fueling dark energy's push on the universe's expansion. Imagine a gravistar, not as a ball of hot plasma or degenerate matter, but as a thin shell of ordinary stuff, encasing a bubble of pure vacuum where quantum fields simmer at their lowest energy state, birthing a constant positive energy density paired with negative pressure of equal strength, a balance so perfect it counters gravity's crush without needing fusion or quantum exclusion tricks. The shell hovering just outside the would-be event horizon, microns away for stellar sizes, so compact that from afar it warps light and time, identically to a black hole, accretion disks, swirling in oblivious imitation, jets blasting out if spinning, yet no true point of no return, no info-losing boundary, just a stable object that could lurk at galactic centers, or roam as stellar remnants, potentially outnumbering black holes if nature favors this route. What sparks this rise isn't just theoretical elegance, but the nagging flaws in black holes, the information paradox, where data seems doomed, the singularities breakdown, where physics quits, and gravistars sweep in as saviors, their interiors a de Sitter space of constant expansion, like a mini-universe inflating forever, pressure negative enough to repel collapse, the shell's tension holding it taut against the vacuum's outward nudge, and calculations show stability for masses from solar to millions, radii a hair larger than Schwarzschild's, say 1.0001 times for thin shells, making them indistinguishable observationally without razor-sharp probes. But here's the thrill. If gravistars replace black holes, they sidestep Hawking radiation's mess. No horizon means no pair production asymmetry. Info stays intact inside the vacuum bubble, retrievable in principle if the shell ever cracks, though in practice, it's as locked away as a safe. Delve into the vacuum energy heart. This isn't empty. Nothing but the quantum vacuum, buzzing with virtual particles, popping in and out per Heisenberg's uncertainty. There's zero-point fluctuations, yielding a cosmological constant lambda in Einstein's equations, positive density, rho sub lambda equals lambda over 8 pi g, but pressure P equals negative rho sub lambda, that negative sign the key to repulsion. Accelerating expansion as observed since supernovae data in 1998, and in a gravistar, this lambda fills the core, sourced perhaps from quantum gravity effects or modified theories, creating a metric that smoothly transitions from interior de Sitter to exterior Schwarzschild, no horizon kink, just a gentle swell, and early models by Mazur and Mottola in 2001 proposed the shell as ultra-relativistic matter with energy density, matching the vacuum thickness delta Ra over Ra around 1/100, preventing collapse while avoiding instabilities that plagued older boson stars or Q-balls, those solitons from scalar fields, and subsequent tweaks incorporated rotation, yielding ergosphere-like regions for energy extraction without naked singularities, or charge, mimicking Reissner-Nordstrom holes, but with finite cores. Engagingly, picture probing one, drop a probe toward it, and unlike a black hole's doom, the shell might wobble under impact, echoing waves differently, or if anisotropic, pressure varying by direction, the light bending shows subtle asymmetries and photon rings, thicker on one side, detectable by upgraded event horizon telescopes, aiming for microarc-second resolution by 2030, while gravitational waves from mergers could ring with quasi-normal modes shifted by the shell's bounce. No clean exponential decay, but damped oscillations hinting at internal structure, and in 2024 simulations by Ito and others, binary gravistar collisions produced waveforms with post-merger echoes, faint ripples bouncing inside the new shell before settling, a smoking gun if LIGO upgrades catch them amid noise, contrasting black holes' smooth ringdowns, tuned to 11 modes for Kerr geometry. This rise ties to broader exotic kin, quark stars, where deconfined quarks stiffen the equation of state beyond neutrons, potentially stable up to 3 solar masses with strange matter phases. But gravastars leap further by invoking vacuum, linking stellar deaths to cosmology's grand puzzle. For if these vacuum bubbles pepper the universe, their collective negative pressure could mimic dark energy's lambda, not uniform, but clumped in galactic cores, explaining expansion without fine-tuning the constant to 1 in 10 to the 120. That infamous discrepancy between quantum field theory's predicted vacuum energy and observed value, perhaps resolved if gravastars sequester most of it, releasing slowly via shell leaks or mergers, a dynamic dark energy, varying over cosmic time, matching supernova and baryon acoustic oscillation data, better than static lambda cold dark matter in some fits. Visualize the birth. A massive star implodes, but instead of punching through to singularity, vacuum energy nucleates at Planck densities, inflating a bubble that the infalling shell coats, halting at near-horizon size. No supernova needed if collapse is gentle, or post-supernova for lighter ones. The remnant core quantum tunneling to gravastar state, evading the Tolman-Oppenheimer-Volkoff limit by negative pressure's cheat code and stability analyses, show thin shells resilient to perturbations, oscillating like drumheads, but damping quickly, while thick shell versions from 2022 papers by Lobo distribute vacuum gradually, smoother metrics avoiding energy condition, violations that once doomed exotics, now compliant with null energy condition via quantum inequalities, bounding negative energy densities over regions. The drama unfolds in binaries. Imagine 2 gravastars orbiting, their shells deforming under tides, merging not with a splash, but a vacuum flood. The combined bubble expanding briefly before new shell forms, releasing gravitational waves laced with vacuum bursts, perhaps gamma flares, if particles annihilate at the interface, and observations like fast radio bursts from magnetar-like shells or ultra-luminous X-ray sources, as gravastars accreting without Eddington limits, their vacuum cores allowing higher throughput, powering some off-nuclear sources and galaxies. As theories evolve, gravastars gain layers, fuzzy dark matter halos around them, if axions condense, or hybrid, with wormhole throats connecting interiors. But the core appeal endures. They heal black hole wounds, preserving unitarity by keeping info in accessible vacuum states. No firewall needed, since no horizon monogamy issue, and Hawking radiation, if any, from shell quantum effects, thermal but info preserving, with entropy still quarter area over Planck, but microstates as vacuum fluctuations countable via path integrals. Across the cosmos, if 10% of compact objects are gravastars, their merger rates tweak LIGO event distributions. Fewer high-mass stellar holes if some turn exotic, and galactic centers like M87 Shadow, imaged fuzzy in 2019, could hide shell wiggles and polarization data from 2023, EHT's linear patterns, revealing magnetic fields, threading the disk, but future 2050 upgrades might spot gravistar-specific brightness asymmetries. This isn't fringe anymore. 2025 reviews in Physical Review D tally over 50 papers yearly on gravastars, from lattice QCD-inspired equations of state to machine learning waveform templates, distinguishing them from holes and ties to multiverse ideas where vacuum bubbles spawn pocket universes. But for stellar scales, they offer a tangible alternative, challenging us to rethink remnants, not as graves, but as living vacuums, pulsing with the universe's hidden energy. Yet the rise hints at even wilder builds, where single gravastars nest within each other, stacking impossibilities. We'll unpack next, as exotics evolve from replacements to nested enigmas, blurring stars and cosmos in ways that make every dark shadow a potential revelation, pulling the narrative from isolated oddities to layered secrets that could redefine reality's rules entirely. Imagine the audacious leap, when theorists, peering deeper into the gravastar's elegant shell, realized Einstein's equations didn't stop at a single vacuum bubble, but allowed for layers upon layers, like cosmic Matryoshka dolls, where one gravastar nests snugly inside another shell, then another, within that, creating a nest, our nested star that defies the simplicity of black holes with its recursive complexity. First proposed in early 2025 by researchers at Goethe University in Frankfurt, led by Luciano Rezzolla and his team, who crunched the math to show stable configurations of multiple thin shells enclosing de Sitter interiors, each layer a gravastar in its own right, the outermost mimicking a black hole's horizon from afar, while hiding a universe of nested vacuums within, pressures balancing across interfaces where ordinary matter transitions to vacuum energy, negative pressures repelling just enough to prevent total collapse. And this isn't mere stacking for spectacle, but a natural outcome of general relativity's flexibility, allowing multi-horizon metrics that smooth out singularities entirely. No infinities to plague the core, just an onion of stable bubbles, where the innermost might be a tiny de Sitter space, expanding forever, separated by shells microns thick, radii differing by factors of 1.001 or so, making the whole object, compact yet finite, a stellar remnant that could form from sequential collapses or quantum fluctuations during supernova aftermaths, potentially explaining why some gravitational wave signals hint at extra wiggles. And consider how this nesting emerges dynamically, perhaps from a single gravastar's shell, fracturing under extreme accretion, spawning inner bubbles that stabilize as new layers, or in the chaotic birth of massive stars, where multiple cores form before merging into a nested structure, evading the pair instability explosions that wipe out traditional remnants in the 20 to 120 solar mass range, allowing nest stars to fill that gap with objects up to 200 solar masses, their layered support distributing mass without thermal runaway. What makes nest stars such a cutting-edge twist is their layered intrigue, each shell contributing to the overall gravitational profile. The exterior Schwarzschild-like, while interiors de Sitter, with cosmological constants, lambda tuned to match observed dark energy, perhaps lambda around 10 to the negative 52 per meter squared, that tiny value driving universal acceleration. And in these models, the nesting stabilizes against perturbations better than single gravastars, shells oscillating in coupled modes that damp quickly, avoiding the thin shell instabilities Oppenheimer and Snyder warned of in 1930s collapse, where bare horizons form nakedly. But here, multiple layers distribute stress, like reinforced armor, and Rezzolla's paper detailed up to 3 nests, with equations showing energy conditions satisfied if shells carry positive tension, vacuum regions negative pressure, the metric continuous across boundaries via Israel junction conditions, jumping discontinuities in extrinsic curvature, but smooth embedding. And for spinning versions, angular momentum distributes across shells, creating nested ergospheres, where frame dragging twists each layer independently, potentially extracting energy in cascades. Penrose processes, chaining through the onion to amplify output, with efficiencies up to 30% per layer, far surpassing single black holes and numerical evolutions in 2025, using the Einstein toolkit, confirmed these spins persist without shedding, shells locking angular momentum via magnetic threading that spans the nests, turning nest stars into ultra-efficient engines for quasar jets or gamma-ray bursts if fed matter. Engagingly, picture a nest star at work. In a binary system, 2 such beasts orbit, their nested structures deforming under tides. Mergers not a simple splash, but a shell-by-shell fusion. Innermost vacuums, merging first in a burst of gravitational waves, echoes propagating outward like seismic ripples in a multi-layered Earth, detectable as prolonged ringdowns with frequencies stepping down through modes. 1 kHz for outer shells, higher for inners, and 2025 simulations by the team predicted these signatures. In LIGO Virgo data, subtle deviations from black hole templates, like extra peaks at merger, or post-merger oscillations lasting milliseconds longer, hinting at internal bounces, where vacuum bubbles collide and rebound, releasing vacuum energy as exotic particles or gravitons, perhaps explaining some fast radio bursts if electromagnetic coupling occurs at shell interfaces, and extend this to triple systems, where a third nestar perturbs the pair, flinging waves in complex harmonics, or in clusters like globulars, nestar-nestar encounters leading to hierarchical mergers, building supermassive versions over giga-years, their wave trains a symphony of nested tones that pulsar timing arrays might catch as low-frequency modulations in the 20-30 nanohertz band. This cutting edge builds on anisotropic gravistars, those where pressure isn't isotropic, but varies radially versus tangentially, inner cores squeezing harder sideways to maintain compactness, outer shells fluffier, allowing radii closer to Schwarzschild without collapse. And in nestars, each layer could be anisotropic differently. The innermost isotropic vacuum, middle anisotropic for stability, outer thin and tense. Models from 2024 by Visser and others, showing such variations, tweak photon sphere locations, making light rings asymmetric, brighter on the equatorial plane due to lensing differences, a telltale for Event Horizon telescope upgrades, where 2030 resolutions might resolve shell edges as faint double rings, polarization swirling in patterns distinct from black hole shadows, helical fields from nested spins, imprinting twists in the EHTs, 2023 data from Sagittarius A*, though noise hides it now. Future arrays like the NGHE8 could confirm, and imagine spectroscopic follow-ups with the extremely large telescope, probing absorption from anisotropic atmospheres, where tangential pressures create puffy equators, emitting broadened lines in hydrogen-Balmer series, shifted by up to 10% from radial uniformity. Quantum corrections add the spice, as in a 2024 paper by Paraki and Karitsis, suggesting nestars bear tiny quantum signatures from loop quantum gravity or string theory, where Planck scale fuzziness smears the innermost shell, preventing true de Sitter purity and introducing modified dispersion relations for light bending. Photons scattering off quantum foam at horizons, delaying arrival times by femtoseconds, measurable in pulsar timing if a nestor orbits nearby, or in gravitational wave propagation, high-frequency modes damping differently. LIGO's 100 Hz sensitivity probing effective field theory corrections, gravity's speed varying with energy per Horava-Lifshitz ideas, and nestors amplify this, multiple layers filtering waves through quantum veils, perhaps resolving the black hole information paradox layer by layer, each shell entangling with the next, info percolating outward without loss, holography extending to nested boundaries, adds CFT generalized to Swiss cheese spacetimes, and delve into those microstates in string theory. Nested fuzzballs count as wrapped brains in Calabi-Yau manifolds, entropy scaling with layer number squared, exceeding Bekenstein-Hawking for deep nests, while loop quantum cosmology predicts bounce echoes in primordial nestars, their formation in the early universe imprinting on cosmic microwave background anisotropies, small angular scales showing power spectrum bumps at multipoles around 1000, testable by Simon's Observatory in the late 2020s. Delve into detection hopes. Gravitational waves top the list, with nestor mergers echoing like thunder in a cathedral. The inner collisions ringing first, outer shells muffling, but not silencing, creating a waveform with harmonic overtones. Not in-Kerr black holes, where only 11 modes dominate, but nestors could excite Dozens machine learning classifiers trained on 2025 datasets from Einstein Toolkit simulations, distinguishing them at 90% confidence. And if 10% of LIGO's 90 events since 2015 are nesters, it tweaks mass distributions, fewer intermediates. If nesting allows heavier stables, while isolated nesters might glitch like neutron stars, but on cosmic scales, shell quakes from vacuum fluctuations, releasing bursts, gamma-ray counterparts to waves if shells crack, tying to Fermi's short bursts, and for supermassive ones, LISA's planned 2037 launch will catch mergers at megaparsec distances, their nested ringdown spanning minutes, with strain amplitudes 10 to the negative 21, resolving up to 10 layers in Fourier spectra, while ground-based Einstein telescope in the 2040s pushes to cubic kilometers sensitivity for stellar nests. Direct imaging beckons too. The Event Horizon Telescope's global array, linking radio dishes worldwide for virtual baselines longer than Earth, imaged M87 shadow at 10 microarc seconds in 2019, but nesters would show wobbly edges, time variable due to shell precession, or nested photon orbits, creating faint inner rings, resolvable with 2050 additions like the Africa array, boosting sensitivity to 10 nanojansky, mapping polarization to trace field lines, threading multiple shells, and for stellar nesters, microlensing events could betray layering, light curves with multiple caustics from aligned shells, durations staggered by hours. Gaia Mission's 2025 data release, hunting such anomalies in million quasar samples, while the Rubin Observatory's legacy survey of space and time from 2025 onward scans the sky nightly, spotting transient nestor flares from shell interactions with interstellar clouds, luminosities spiking to 10 to the 30 ergs per second in optical bands. Spectroscopic twists emerge in accretion around a nestar. Infalling gas might hit outer shells first, heating to X-rays, but leaking some through thin gaps. Spectra with absorption lines from shell atmospheres, helium or hydrogen, if ordinary matter lingers, broadened by Doppler from rotations up to half-light speed at equators, unlike black holes' smooth continua, and ultra-luminous sources like Holmberg 9b, 1,000 solar luminosities without Eddington limit, could be nestars siphoning efficiently, vacuum cores absorbing without feedback blowouts, jets collimated by nested magnetic cages, precessing in helical paths observed in VLBI radio maps, and X-ray telescopes like Athena, launching 2028, could resolve shell edges via iron line reverberation. Time lags between direct and reflected emission, revealing layer depths, delays of microseconds for inner shells, mapping the onion in active galactic nuclei. Cutting-edge theories push boundaries like massive gravity nestars from 2025 extensions, where gravitons gain mass via Higgs-like mechanisms, modifying long-range forces without ghosts, allowing stable exotics without exotic matter, energy conditions upheld, and in these, nesting prevents Boulware desert instabilities, black hole alternatives that evaporate cleanly, while brane-world nesters and Randall-Sundrum models place shells on higher dimensional branes, are 4D universe a projection, vacuum energy, localized to layers, explaining hierarchy problems from Planck to TeV, scales, and extra-dimensional nesting, allows Kaluza-Klein modes, gravitons with momentum in compact dimensions, appearing as massive particles in our view, potentially detected at LHC upgrades, probing energies up to 14 tera-electron volts, with missing transverse energy signatures from nestar-induced black hole production in high luminosity runs. The fascination swells with cosmological ties. If nestars dot galaxies, their nested vacuums contribute to dark energy dynamically, inner bubbles expanding faster than outers, collective lambda varying with redshift, matching Hubble tension, where local measurements at 74 kilometers per second per megaparsec clash with cosmic at 67, perhaps nestar clustering in voids, boosting expansion locally. and mergers across cosmic time seed the stochastic background. Nanohertz waves from supermassive nest stars detected by pulsar arrays like IPTA in 2024, but with nested echoes adding structure to the spectrum. A comb of frequencies hinting at layers, and in large-scale structure, nest stars as seeds for galaxy formation. Their gravity wells deeper due to layering, attracting dark matter halos preferentially, explaining biased clustering in 2025 DSE baryon. Acoustic oscillation maps, where voids show underdense nest star populations correlating with expansion anomalies. Visualize probing one up close. A spacecraft nearing the outer shell feels gravity ramp, like a black hole, time dilating to crawls, but no freeze at horizon. Instead, a subtle bounce from shell tension, electromagnetic probes scattering off vacuum fluctuations, Cherenkov-like radiation from virtual pairs, while neutrinos stream through unimpeded, their fluxes higher from inner cores, ice cube detecting upward events from galactic nesters if aligned, and particle detectors might catch sterile neutrinos or axions leaking from vacuum decays, energies in kilo-electron volts, tying to XE0 dark matter searches that in 2024 hinted at sub-GeV signals unexplained by WIMPs. This isn't stopping at 3 layers. Theoretical limits allow dozens, each adding compactness. The innermost, a Planck-sized de Sitter seed from quantum nucleation, building outward in hierarchical collapse, and stability, holds if shell thicknesses taper, delta Rho decreasing inward, pressures matching at junctions via stress-energy continuity, and for charged nesters, electrostatic repulsion between shells adds support, mimicking extremal black holes, but with finite charge radii, allowing higher spins without nakedness, Kerr-like parameters, up to 0.99, and in magnetized versions, fields threading nests create dynamo effects, amplifying to 10 to the 15th Gauss across layers, powering recurrent flares like soft gamma repeaters, but on stellar scales, observable as variable radio sources in ASCAP surveys. As observations sharpen, nest stars challenge the paradigm. 2025 ALMA submillimeter views of Sagittarius A star's corona might reveal shell-induced flaring, irregular at infrared wavelengths, while JWST's deep field spot early nest stars as overbright point sources in reionization era, their vacuum glow piercing dust, and future Einstein probes X-ray monitors catch shell quakes as variable transients, durations seconds to minutes, with light curves showing nested decays, exponential but stepped, hinting at layer-by-layer energy release. The twists keep coming. Hybrid nesters with quark matter in middle layers, stiffening against crush, or fuzzy dark matter condensates as outermost halos, axion stars nesting gravistars, multi-scale structures, resolving small-scale CDM issues, and in quantum information views, each shell a quantum error-correcting code, protecting inner vacua from decoherence, info flowing radially like a neural net, black hole interiors reimagined as nested qubits, with entanglement entropy saturating at each boundary, computable via Ryu-Takayanagi surfaces, generalized to multi-horizon spacetimes. Across the universe, if nesters comprise half of compact objects, their evolution alters stellar populations, fewer traditional black holes, meaning less feedback in galaxies, smoother star formation, and merger rates fitting LIGO's observed void over densities, while primordial nesters from inflationary bubbles could be dark matter candidates, masses from grams to stars, evaporating slowly without gamma spikes, their relic density matching omega sub-dark matter at 0.26 from Planck 2018, but with nested variants allowing variable masses, evading microlensing constraints from HSC Subaru surveys. This layered revolution doesn't just tweak stars, it rewrites the cosmos, nest stars as microcosms of multiverse foam, where vacuum domains nest infinitely, our universe one shell in a grander onion, pulling us from stellar remnants to existential depths, where cutting-edge math unveils not endings but endless beginnings, teasing that the universe's rules hide recursions, we've only begun to unwrap. And as future telescopes like the Habitable Worlds Observatory in the 2050s peer into exoplanet atmospheres around nestar systems, they might detect anomalous abundances from vacuum-sourced elements or gravitational microlensing by rogue nestars wandering the halo, light curves with recursive caustics, revealing the onion's depth, forever expanding our grasp of the star's true nested nature. As we draw the curtain on this cosmic odyssey, through the lives and deaths of stars, from the steady hum of ordinary fusion engines like our Sun, to the cataclysmic births of white dwarfs, neutron stars, and the enigmatic black holes that once seemed like the universe's final punctuation marks, we've journeyed into realms where physics bends and breaks, only to reveal exotic alternatives that whisper of deeper harmonies. And now, with nestars and their layered mysteries unfolding like infinite Russian dolls, powered by the very vacuum energy tearing the cosmos apart, it's clear that stars aren't just balls of gas or collapsed remnants, but dynamic architects of reality itself, challenging us to rethink not only their endings, but the fabric of existence, a narrative that began with that simple balance of gravity and nuclear fire, where hydrogen atoms smash into helium in cores, hotter than 1,000,000 suns, sustaining equilibrium for billions of years, allowing planets to orbit and life to bloom under their glow, yet inevitably tipping when fuel depletes, outer layers puffing into red giants that could one day swallow Earth whole, shedding nebulae like ethereal veils before exposing dense hearts propped by electron degeneracy, those quantum rules forbidding overlap in a crush, so intense a thimbleful weighs tons, stable up to 1.4 solar masses before relativity weakens the shield, forcing collapse to neutron realms, where exclusion now guards neutrons in a soup denser than atomic nuclei, spinning beacons pulsing radio waves across the galaxy, their magnetic tempests flaring as magnetars or recycling into millisecond timers, precise as atomic clocks. Yet even these titans falter beyond 2 solar masses, imploding to black hole thresholds, where space-time folds into inescapable wells, horizons cloaking singularities that defy equations, birthing paradoxes like Hawking's radiation puzzle, where information seems lost to evaporation's fire, clashing quantum purity with gravitational tyranny. And from these shadows emerged gravastars, vacuum-cored shells mimicking horizons without the doom, negative pressures repelling collapse in de Sitter bubbles, tied to dark energy's push, stable and info-preserving, then nestars stacking them recursively, multiple layers smoothing infinities with coupled oscillations, their mergers echoing in waves that future detectors might catch as harmonic symphonies, hinting at a universe where stellar deaths spawn nested infinities rather than voids. This evolution isn't just academic fireworks. It's a profound shift in how we see the cosmos. For if black holes were once the ultimate mysteries, swallowing light and secrets alike, these exotics suggest nature abhors singularities as much as vacuums, preferring layered stability where vacuum energy, that cosmological constant lambda once dismissed by Einstein as his biggest blunder, now powers not just universal expansion, but stellar remnants, potentially resolving the Hubble tension with dynamic contributions from clumped nestars and voids, accelerating local measures to 74 kilometers per second per megaparsec, while cosmic averages hold at 67. And imagine the implications for galaxy formation, where supermassive nestars at centers seed ordered spirals not through destructive feedback, but gentle vacuum tugs, aligning disks without quenching stars prematurely, allowing more habitable worlds to flourish across the Milky Way's arms, our own sun. A modest player in a galaxy harboring billions of these layered beasts, their collective negative pressure easing the fine-tuning nightmare of lambda at 1 in 10 to the 120, that quantum field prediction versus observation clash, perhaps sequestered in nested cores, leaking slowly over eons, engagingly reflect on the human drama woven through this tale. From Chandrasekhar's sea voyage epiphany in the 1930s calculating white dwarf limits amid skepticism, to Hawking's wheelchair-bound insights in the 1970s, betting against his own paradox only to concede, and now Rizzola's 2025 models pushing nest stars into simulations that run on supercomputers, rivaling the human brain in complexity. Each breakthrough a testament to curiosity's pull, turning night sky wonders into equations that predict waveforms we detect with lasers a kilometer long. LIGO's mirrors, trembling at 10 to the negative 19 meters from waves born a billion years ago. And as we ponder these, the ordinary stars shine anew, not as precursors to doom, but inspirations for resilience, their fusion chains, proton-proton for sun-like CNO cycles, for heavies, forging carbon and oxygen that build our bodies, a stellar legacy in every breath, while white dwarfs cool to black over trillions of years, outlasting galaxies. Neutron stars glitch and spin like cosmic metronomes, timing the universe's rhythm, and black holes, if they persist, merge in gravitational ballets detected across voids. But exotics like gravastars and nest stars elevate this to poetry. Shells of matter dancing with vacuum infinities, potentially hosting quantum computers in their entangled layers, info flowing radially without loss, resolving paradoxes by design, and observationally, the hunt intensifies. Event Horizon Telescope's global eyes on Sagittarius A star, seeking shell wobbles in its fuzzy ring. James Webb, peering at early quasars for overbright nest star, glows, piercing reionization fog. LISA's space-based arms in the 3040s, catching supermassive mergers with nested echoes, spanning octaves, while ground arrays like the Square Kilometer Array map radio pulses from potential nest star glitches, their periods stepping like staircases from inner spins. Yet, beyond detection lies wonder. What if nest stars connect to multiverse foam, each inner bubble a pocket universe inflating eternally? Our Big Bang one layer in an endless stack, vacuum decays tunneling through shells to birth new realms. Or if primordial nest stars from inflationary seeds form dark matter's bulk, asteroid mass ones, microlensing stars, subtly, lunar-sized evading gamma bursts from evaporation, their relic dance explaining galactic rotation curves without new particles. And in this view, stars' deaths aren't tragedies, but genesis, ordinary balances, evolving to exotic nests that propel cosmic acceleration. Dark energy, not a constant but a stellar symphony, varying with merger rates, peaking at redshifts around 1, matching supernova light curves and cosmic microwave anisotropies from Planck's 2018 maps. Those temperature fluctuations at 10 to the negative 5 Kelvin, whispering of nested seeds in the first instance. Picture standing under the Milky Way, that band of 100 billion stars, many destined for these fates, red dwarfs sipping fuel for trillions of years, becoming helium white dwarfs without fanfare. O-type giants blazing brief but fierce, exploding to neutron or black hole paths, but now with gravastar branches, perhaps 90% swerve to vacuum shells, their jets carving bubbles in interstellar gas, seeding molecular clouds for new births, a cycle where death fuels life eternally. And for us, this knowledge empowers, inspiring technologies from pulsar navigation for deep space probes to quantum sensors, mimicking degeneracy pressures for ultra-dense computing or vacuum energy, taps from lab analogs, sonic black holes and fluids radiating phonons to harvest negative pressure, inching toward unlimited power. The paradoxes that once haunted, information lost, singularities raging, fade in Nestor's light, each layer a safeguard, entanglement weaving through shells like threads in a tapestry, unitary evolution, preserved as vacuums entangle without horizon's monogamy woes, and Hawking radiation, if present, emerges from shell fluctuations, thermal spectra encoding microstates, countable via path integrals over nested metrics, resolving bets and debates in a flash of elegance, while cosmic censorship holds firm. No naked infinities, but veiled nests, geodesics completing through layers rather than terminating, Penrose diagrams showing infinite interiors without chaos. As telescopes evolve, from Roman Space Telescope's 2027 wide-field hunts for rogue nesters to the Habitable Worlds Observatory in the 5040s, scanning exoplanets around these exotics for biosignatures altered by vacuum leaks, perhaps exotic isotopes in atmospheres. We edge closer to confirmation. Light curves from microlensing campaigns, like Ogull's million events, revealing recursive dips, durations hours to days with nested revivals, or X-ray echoes from Athena's 2028 gaze on active nuclei, iron lines reverberating off inner shells with lags tracing depths, and if verified, Nestars rewrite textbooks, stellar evolution branching to vacuum paths for masses above 8 solar pair instability gaps filled by layered supports. LIGO's mass deserts explained as Nestar clusters, their waves chirping differently from pure holes. This conclusion isn't an end, but an invitation, urging you to gaze upward, not with finality, but anticipation. For in every twinkling point lies a story of balance, collapse, and rebirth. Ordinary stars teaching equilibrium's grace, their deaths birthing exotics that mirror the universe's expansion, dark energy's repulsion echoing in nested vacuums, and perhaps, in the grandest twist, our reality a Nestar itself, one layer in an infinite stack where Big Bangs cascade forever, pulling us from stellar hearths to cosmic infinities, where the wildest challenges to physics aren't threats, but triumphs, revealing a universe not of voids, but vibrant layers, endlessly engaging, profoundly alive,